Our next speaker is Harry. Harry recently moved from Microsoft Research to Alibaba, where he's starting a cool new research group on networking. So he's excited to talk about that as well. And then before Microsoft, he got his PhD from Yale, and he has worked on a lot of interesting ideas in the field of ultra-low latency networking, network management, wide-area networks, and obviously fault tolerance. And in this work, he's going to present his work on forward fault injection.
Thank you for me. Thank you so much. Thank you for inviting me here. I found that I'm the only industry speaker. Yeah. So, yeah. But I didn't show any affiliation here because this work is done actually during my PhD and when I was interning with Microsoft Research. It's 5 years ago work because I picked this to match the theme of this workshop because after graduation, my research style suddenly changed from theory to system. And actually, this is a good kind of related work talk because before this talk, there are 2 talks talking about this and comparing with this. And the performance of this seems to not very good, but I believe people have might have some misunderstanding, and yeah, I will try to explain. So, and today, after my CCOM talk, I think this project also have some breakthrough, and I think this is the first time we reported to the audience, the improvement of the algorithm. So it's called traffic engineering with forward fault correction, and the concept this paper create is the FFC concept. Later I will explain. So here's the roadmap of this. So I think the first item can go very quickly because I think everybody understand, and then I will introduce what kind of network faults I care about, and what is the concept of FFC, and then how to realize FFCTE, and what's the performance of that. So yeah, we can go over this very quickly. So as a cloud provider, I can seriously say that we're facing the problem that where our business is growing. For example, our next year's plans profit is double this year. So if you want to double, you need to carry more customer. You have more infrastructure to build, and the infrastructure is really expensive. So we want to really use it very efficient. And for a network, people come up with idea that how to make it highly utilized, but still guarantee the reliability and the performance, right? And before my work, there already a trend that from industry that building the centralized TE to optimize, especially one. So both Microsoft and Google has their own solution. And this slide just briefly explain why people want to build a centralized TE rather than distributed TE. The one thing is that at that time SDN is hot. The other is that we find that the centralized TE has much more efficient, much better efficiency. For example, given this network, the link capacity is 10, and if we do the traffic engineering in a distributed way, that when the red flow arrives, we give 10, and but when the green flow arrives, we only have 5 to give, so that the total throughput is 15. But if we have a global controller and we have global view, we can just re-optimize everything so that the throughput can be higher. So that this is the reason why people rely on centralized TE. And the overall architecture is, we have a centralized TE controller, and then here's a network. And we need to build all the monitoring stuff to form a network view to feed to the controller. And then the controller have computation and just configure the network with all kind of configurations distributedly over the large scale network. And so if ideally, this system is easy to build, and it can work quite well, but but in large scale in production, things is not that smooth because in reality the network has all kind of faults, and in today's talk, people talk about the data plane faults like link failures, switch failures, and also we found when we built the system inside Microsoft, we also found the failure like the configuration failure, which means that in a large scale network, when you want to send all the configuration to all the switches, which is hard to guarantee that all of them all the configuration just succeed. So from time to time you will find that only a large portion of the switches got the new configuration, but others just have some failure, and we call it control plane fault. That can also create a very big problem. So we want to handle this. And the second part is that, let me just explain what's the fault and what happened after the fault happened. For example, we start from the data plane fault, which is link failure or switch failure. And here, which is explain what Monia says that, about how device react to the failures when failure happen locally. For example, given this network and traffic, there are two flows, green flow and the blue flow, and they are both using two paths to forward to destination, which is S4. And they're splitting the traffic in this way, 7 and 3. And when a failure happens, what happens next is that the S2 will find the link failure, and then it will remove the path from his candidate path, and then there is only one, right? And what it does is the rescaling, which means it will proportionally rescale based on the weight of the residual path and send traffic in the residual path. And in this simple case, is that it will resend all the traffic via the path S2, S1, and S4 for the blue flow. And of course, after the rescaling, there will be congestion. This congestion can be fixed next time when the global controller reconfigure everything, right? But during this period, for example, 5-minute period, the congestion will just keep happening. Yeah. This is the congestion caused by data plane faults. And we also have control plane fault, which means when you configure the switch, due to all kinds of failures like RPC failures, and the switch might have bugs, have the shortage of the CPU or memory, and it can fail. And when it fails, it means that one part of the network is using new configuration, the other part is using old one, and the mismatch will create congestion. And you can refer to paper about the concrete example. Now I just give you some the idea, which means that in the reality, when we build this system, we can find that we rely on the network view and network configuration, but the network view is not accurate because during next 5 minutes, failures can happen, and the network topology can be changed, and also the network configuration is not complete because of the failure of the configuration. That both of them will create problem that we need to solve. And this gives you some idea about how frequent this fault happen. And this is also from Microsoft 1. And we find that if we divide times by 5 minutes, you can see that about 25% of the time, in the 5 minutes period, there will be at least one link failure. And also, when you reconfigure the whole network, there will be up to 1% of the probability that you cannot successfully send your new configuration. And because the goal of the traffic engineering system is to highly utilize this, so that when you highly utilize the system, when anything happens, it will trigger severe congestion. And for example, here we just do a simulation on the Microsoft 1, so that this shows how much it exceeds the highest highest utilized link, how much it exceeds to the capacity. And here's the CDF. You can see that it can trigger very severe congestion once things happen. Then, just because of the faults, so that's we come to the definition of FFC. So let me explain you how we get into that concept. So before FFC, there are basically two ways. One way is heavy over provisioning that is also mentioned by Monia, that we can just leave a very big headroom, and hopefully when things happen, when traffic gets rerouted, so the headroom, the spare capacity can hold. So, but the problem is that it's a big loss of throughput, and you still don't have guarantee that whether the congestion will be avoided or not. And the second is a reactive approach. Right? For example, when you find some failure, you try to tell the controller, and the controller recompute something and reconfigure the network to fix that. That means, this kind of control loop has kind of three flaws. One is that you cannot prevent congestion from happening, and how quickly you resolve the problem depends on how fast you can react from the controller. But just as I said, the controller uses 5 minutes to reconfigure the network has a reason, because in large-scale network, the controller cannot do that really fast. And also, you are facing, when you reconfigure the network, you are facing the control plane faults. And sometimes you want to react, but you have the control plane failure that prevents you from doing it. So that's the disadvantage of the reactive approach. So then we think about can we be more proactive? But be more proactive is that every time TE controller, every 5 minutes TE controller compute a kind of a configuration, and now the configuration only valid during the current time, right? So in the current snapshot. But can we just compute the configuration, add some robustness into the configuration so that when I configure the network, the configuration itself has some ability that when things happen, the configuration can locally fix the problem until next time. Until next time, the TE updated the global network. Can we do that? Right. So when we think about this, so we have a bad news and good news. So the bad news is that we really find that where exactly the next 5 minutes, where exactly the problem happened is really random. We cannot actually find, other than using the probability. At that time we're not using any probability. We just it's purely random. We don't have any clue. But the good news is that we find in 5 minutes period, the number of simultaneous failure should be very rare. The number should be small, right? And this just for this kind of scenario, so we just provide a concept called FFC, which is forward fault correction. What is saying that whether I can come up with a routing plan. The routing plan has some robustness. The robustness is that it can guarantee there is no congestion if the number of faults is under a parameter k. Can we do that? So this is not, in conceptually it's not new, because if you aware of some other techniques like forward error correction in the communication, right? It just say that if the channel is lossy, and whether I can just send 10 packets, but if only 9 packets get to the destination, I can recover all the information, right? I think this kind of philosophy happens everywhere, but it first happened in the traffic engineering domain. That whether I can have traffic engineering, you have this property. And so let me show you an example that this kind of traffic engineering does exist. So for example, given this network, and there are 2 flows, green and blue. They are using 2 paths, and I would say this is one FFC traffic engineering with k equals 1, because this is resilient to any single link failure in this network. For example, if I fail the link from S1 to S2. And after the rescaling, you can see there's no congestion. And if we fill the link from S1 to S4, no congestion. And if we fill the S2 to S4, no congestion. And due to the symmetric, you can see that any single link failure cannot break this, cannot cause any congestion. Yeah. That means this just shows you a case that this kind of traffic engineering exists. What matters is how I'm going to find it systematically. Okay. And before that, I would say there is a kind of a trade-off. And because suppose the blue flow and the green flow has maybe 15 unit demand. And the traffic engineering here, it does not have any FFC guarantee. Right? And the traffic engineering at the bottom also does not have any guarantee. But what we can observe is that if we compare these two, what they're saying is that if I want to achieve FFC, I do have some sacrifice on the throughput. That's why the later work shows that, okay, I have the throughput loss, but the throughput loss is kind of a price that I pay for the robustness. But the price cost is not for sure, because if we compare these two, their throughput are the same. But just because of the different traffic engineering, they have different kind of robustness property. And what we want to do is that we want to find a very good FFC traffic engineering that it can have the property, but it can also, under this property, it can also maximize the throughput. Okay. And then now I reached the point that I introduced how to realize FFC. Now, from the system part, we are coming to the theory part. And you will find that from this kind of practical background, we finally reach I personally think it's a very beautiful setup of the linear programming problem. Let's start. So now we need to solve two problems. One is how we merge the FFC requirement into the current TE computation framework. And then is how to find the FFC TE. So as we said in the previous talk also, so we basically, the basic formulation of the traffic engineering is simple. It's basically multi-flow commodity optimization, right? They have regular kind of objective and constraints. And if we translate it, they are in this kind of form. But of course, if you only have this, you cannot guarantee that your TE has FFC guarantee. And what's the FFC guarantee? We will encode this FFC guarantee into some we call FFC constraints. They are also linear constraints, but what they require is that under K control plane failure, under KE link failure, and some switch failures, there's still no congestion. These are the linear programming constraints I will add into this. And this overall is the FFC TE formulation. Then the problem is first is how we encode this. Right? And the beautiful part is that no matter it is control plane fault or link fault or switch fault, finally we find they are sharing a kind of same abstract format. Let me explain it to you. So let's take link fault as an example. So in the computation, what I say is that if the FFC require is resilient to any single link failure, it basically means that after path 1 goes down, our allocation of the bandwidth is sufficient for the flow size, right? And if path goes down 1 and 3, 3 goes down 1 and 2. Basically, we will add this kind of constraint to our linear programming. this is a kind of a necessary condition for us to achieve our goal. But surprisingly, this is also sufficient, which means that we have a lemma saying that if finally we add this into our TE formulation and we finally get A1, A2, and A3, what we need to do is just use this kind of weight to forward traffic among path 1, path 2, and path 3. And that is sufficiently guaranteed that the FFC property is achieved. That is one thing that I love. And then if we generalize it, you will find that, if we have, for example, if we have n paths and we want to resilient with k failures, that means that from here, that means that we have 1, 2, 3 variable, and we require any two of the 3 variable sum is larger or smaller than some kind of constraint. Right? So that if we extend it, so in this case we have 3 choose 2 constraint, but in general case we have n choose k constraint. Right? So that this is FFC's constraint. What they're saying is that if we have n paths and their allocation is A1 to AN, and if we require FFC that is resilient with k failures, that just means that we require any n minus k elements sum is larger than a flow size. Yeah. So that overall we have, for this single flow, we have n choose k.
Are you describing the constraints in the special case when the paths have no shared links?
Yeah. So currently I'm saying about the link disjoint paths. Yeah. So this is the problem we are facing. So generally, if we just naively encode the FFC constraint, the problem we are seeing is that the exponentially many of the number of constraints that the solver cannot solve. So yeah, this is what our problem. And then the key question is that, is there any way for us to compress the FFC constraint so that we use a small number of FFC constraints to represent the original one? And by lossless, what I mean is that during this process, I don't make any kind of simplification or pick the subdomain of the physical space, right? Which kind of lower the throughput. We don't want to lose any throughput or optimity of the throughput, but we want to use really small number of constraints to represent the original one. How can we do that? So in the original paper, we have a proposal and using sorting network. And I once really proud of that, but later, some smarter guys propose another one that is even better. But we start from here, and today I will talk about both. So the first approach is using sorting network, and then I can achieve a lossless compression from n choose k to n times k. And the idea is inspired by this. So basically, first we do a equivalent transformation. Is that this is just saying that if I know ym, which is m's largest element, that this single constraint will represent this. Right? Then the problem is that how can I use x1 to xn to represent the ym? Yeah. If we can do that, and with this constraint, we can achieve our goal. Yeah. And how to do that? So the key idea is a sorting network from circuit design. In circuit design, there's a gate which we call comparison gate, that you have 2 input, they give 2 output, and they always put the max of the 2 input on the top and the minimum on the bottom. Okay. And if we can achieve this in the linear programming, that means that we can introduce 2 new variables. One is representing the larger of these 2. the other is the smaller of these two. And with this gate, we can kind of build a circuit. Right? For example, if I first run, if I introduce Z1, Z2, and then Z2 is the larger of this, and then I build Z4, and the Z4 is actually larger one of these three, right? Then it can be continued. And after one pop, I got Y1. Y1 actually represents the first largest among these four, right? And then I can do it again. And then I pop the second largest one, right? If K is 2, and then I'm done, right? I can just stop here, and finally, I require Y1 and Y2 is smaller than this constraint, and then it's done. So overall, because I'm doing like a pop sorting, I do it for K times N times. So the complexity is K times N. We introduce some extra variable and extra constraint, but it's really worth under large scale. So this is and then we can also see that during this process, we didn't make any kind of approximation, and then the throughput should be optimal. Yeah. But yeah, after I published this paper, and I found a problem. This problem just confused me a lot, and the problem is from that, how are you going to encode this to the linear programming format? And actually, there's no accurate way to do this, because if I make a transformation, from here to here is equivalent, right? But there's no way to represent this. And in linear programming, what I can do is to use this kind of linear constraints to represent this comparison gate. And then the problem is, if I do this approximation, whether the whole kind of conclusion is still valid. Right? This is something I realized after I published that paper. And at that time, it's a hard time, because I might decide to withdraw this paper, without reasoning about this. But at that time, I find that in the code, it works really well. At that time, I could not explain it, but it's worked really well. And I tried all the kind of cases. And then I think about the proof. And I'm really happy that finally I got the proof. And it has been read by multiple people. And I think that's valid, so that this kind of approximation indeed works well, perfectly well, in this kind of setting. And I provide this proof in my web page. If you are interested, you can see. Then I decided not to withdraw this paper. Okay. Then when I presented at different university, and one day when I presented, and after the talk, some theory guy told me that do you think this is optimal? I think I think I come up with this idea really for a really long time. I think there's no better way, but he said that there's a better way. So yeah, the better way is doing it with n. So you even don't use k, and this is come with the next solution using strong duality that we can compress this to O(n). How do we do that? I think it's the first part is still here. So we have n variable, and we define a function that this is the sum of the largest k elements, right? And the first one is that we define linear programming. This is something I learned. I think it's amazing. So we define a linear programming, and now we treat x as a parameter rather than variable. So given each fixed x, so we have this linear programming, and the yi is within 0 and 1, and their sum is k, and this is time, because this is parameter. So this is still linear programming, right? And the fx is actually the optimal the optimal object value of this linear programming. Are you with me? Yeah. And then the beautiful part comes. So if we make a dual of this, so this is the dual of this problem. And because this is linear programming, it follows the strong duality, which means the maximum value of this problem is equal to the minimum value of this problem. Okay. Which means because of strong duality, fx, which is the maximum value, is equal to the mean of this. And we can do this. So if we write a constraint that is this part is always smaller than b, then it's sufficient to say that the minimum of this is still smaller than b, right? And the minimum of this is what? It's fx. So if we write this, it will just sufficiently guarantee that fx is smaller than the bound, which means the sum of the largest k elements is smaller than the bound. So that, of course, this is also need to have this kind of side constraint. So if we put this together, this will be sufficient to guarantee this. And if you count how many variables and constraints this formulation have, is 2n. So then it's get improved. So I got really learned. So then I learned, this is the first time for me to learn how useful is duality. Yeah. Of course, this is n. Okay. The final part is the performance of FSTE. The evaluation is done with testbed, and also the large-scale simulation. So today I will show you the result of large-scale simulation. And we do two kind of network. One has single priority. I think the most interesting part is the multiple priority traffic. Here, what I'm showing is this bar shows the data loss. Data loss means the more data loss we have, the more congestion we have. And we compare with the data loss, the congestion with FFC and without FFC, and the throughput with FFC and without FFC. First, this is the result of single priority. And you can show that under that case, so we significantly reduce the congestion, but still keep the near optimal throughput. Is this. And that's because during that time, maybe the traffic is not really busy, so we have plenty spare capacity. And when you have spare capacity and when you use FFC to smartly lay out the traffic, I think that's fine. There's no throughput loss. And then we see the different priority traffic. So we have high priority traffic, medium priority traffic, and low priority traffic. So for each time when we do the computation, we first compute the high priority traffic. And when it's done, we remove it from the network and the relevant link capacity and compute for the medium priority and the low priority. And the beautiful part here is that you can find, FSC offer you a knob that how important the traffic is. If the traffic is really important, you can use larger k. For example, you use k equals to 3 for the really very strong guarantee that it has no congestion. And the one is low priority. You even don't use FFC traffic because you don't care whether it's congested or not. Right? So it offers you a kind of quality of service in the traffic engineering. And then what you can say is that because of the really strong guarantee and the high priority traffic congestion is really low. And but the throughput is still optimal. That's because the high priority traffic is not bandwidth hungry. For them, so the network is plenty empty. And what matters is how you lay out the traffic to make it more robust. Right? And also the medium priority, you have a little bit throughput loss. And what's interesting is for the low priority, we have a little bit throughput loss, but you have a lot of loss here. So you can see that how we use FFC as a knob to tune the trade-off. You know, for high priority traffic, we just guarantee that it has a high throughput and low congestion, but the price, who is paying the price? The low priority traffic is paying the price. And the price they're paying is the congestion, which is we don't care. Right? So this is interesting. So here we come to the conclusion is that we start from a very practical kind of problem, and then we formulate it as an FFC constraint, which is just give you n variables, and you require any k of them, the sum is larger or smaller than some kind of value, and how can you compute it efficiently? And today I introduced two kinds of methodology. One is sorting network, the other is using strong duality. And then with the real network traffic and the topology, we can see that it's not just a traffic engineering traffic engineering computation. It's actually offer you a knob. This knob is new, so that you can, based on different kind of traffic priority, based on your need, you can tune the trade-off between throughput and the congestion to get what you want and pay what you want to pay. So yeah, I will stop here and happy to take any question. Thanks.
Question, Jim. So was there an application where you applied this and proved it in a data center?
Currently?
Any time in the past or future?
Not yet, because it's for wide area, yeah. But not yet. There's no real system now taking this approach yet. Basically, what I'm understanding is that they have even more practical issues to worry about, rather than this, traffic engineering algorithm. Yeah.
So I guess we had a very fuzzy discussion, but it's surrounding sort of the combination of FFC versus some of the scenario-based stuff and some of Gen stuff from the morning. So and we were not sure how all of these things fit together. So does one preempt the other? Right? I mean, the question is, if I had FFC and a purely data plane solution, does the data plane solution always strictly, is it better? Or, for example, also FFC is paying a cost for sort of having to pre-compute and store, and sort of basically paying the congestion cost and so on. So wondering whether there's a different way of saying, maybe if you use an FFC logic to pre-compute different solutions for different failure scenarios, keep them in the switch and rapidly fail over. Use a distributed solution to learn which failure mode you are in, and then rapidly switch over using some of Gen's protocols or other kinds of things. And again, it fits into some of what Manu was saying about scenarios. We were just trying to fuzzily discuss how these all things fit together, or is one strictly better than the other, where if you have FFC, you don't need anything else. Or if you have Gen solution, you don't need anything else. I don't know.
It's a great question. But first of all, I sometimes also wondering whether I can put everything together. The answer is, you cannot put everything. You publish in CCOM and then SDI together. you finally got to have a way to proceed. And so in this, I think in the whole picture, so there are several decision makers, right? One is how to select the path. And I think what Jen's doing, basically, one thing is how to select the path, right? And FFC is not doing that. It's just FFC just define, okay, you have link disjoint path. That's enough. And also, in this picture, there's also one thing that is missing is the congestion control, right? You do kind of path selection, and you do traffic engineering, and on top of this, there's also congestion control. And they're kind of basically working together. And what I can say is that,
So if I have multi-path TCP, is all of these related?
yeah. So they kind of,
TCP also into the mix.
yeah, they kind of mix together. If you want to dig it even further, is that there is also a networking design problem at first. You first designed this, select the path, decide how to divide the weight, and then do the congestion control, right? And I think at different layers, you will have different proposals. But yeah, if you ask how to fix them together, I'm just saying currently I think design is doing very independent way, and the path is currently is using very simple kind of strategy to doing path and simple algorithm to do traffic engineering, and then you use TCP. This is the art how they fit together, and all the new proposals are just trying to improve one part of this. But of course, I agree that new proposal maybe cannot fit together because they are not nobody is fitting them together yet. Yeah. Yeah, I also thought that. You know, when I was junior graduate student, I was wondering, so you propose this, you propose that, how can we put them together? But later I realized you don't have to.
So you presented a method using strong duality and another one using sorting networks for optimizing over traffic allocations on link disjoint paths when the number of faults is less than or equal to k. Have you considered the general problem where the paths may overlap? And is there an extension of these techniques to handle that case?
Oh, great question. So here I showed the easy, kind of easy case that is link disjoint. But in the paper, we show that you can also have some variation, like each link only take 2 paths, or 3 paths, or 4 paths, to kind of create your diversity of your paths. But still, we have some guarantee that one link goes down, I can know how many paths go down with it. Right. So that and that can also easily to fit into the framework.
So you assume that the different mega paths are given as input. And when there is a failure, I guess you send a failure notification to the source node.
Yes.
Right? So can you actually apply your technique directly at the node where you have the failure? Similarly, somehow to add tree, which was also a CCOM paper. So can we apply your technique? But now we want to load balance the traffic when there is a failure at the node when the failures occur, so that we don't have to send the notification and drop the traffic in between.
Yeah, that's a very good question. So I thought about that when I did this work. And finally, I took this tunnel approach, is that the source have more ability to redistribute the traffic. So I think the FFC framework can be used in your framework, but you will find that the efficiency is low because in the intermediate node, it can only control how it forwarded the traffic to the further node, right? It cannot control how the traffic come to it, right? Then it will just reduce the selection base and the flexible base for you to search the good solution for the throughput. And in the extreme case that in the intermediate node might not have any downstream node to forward the traffic. And then there will be a black hole.
So I can still use the same technique, this lossless compression, applied on the, let's say, the backup paths on each link.
Right.
And then okay, that's good.
Okay, any last questions? Great, let's thank you very much.